All right, so now that we know Ohm's law and these patterns across series and parallel circuits, whenever you look at a circuit problem, we can combine those two theories into a method of solving these circuit problems that I like to call the VIR table method, or VIR table method. So when you see a complicated circuit, even a simple one, I recommend you set up a table like this, which if you look at the top, we have the voltages, the currents, and the resistances. We want to know what those values are for each resistor we have in the circuit. So when we set up a table like this, if I had two resistors, I would label them R1, R2, and then the total, also known as R equivalent. If I had 5 resistors, I would keep going. I'd have R1, R2, 3, 4, 5, and then the total. So to fill this in, it's almost like a Sudoku puzzle where we can use those series and parallel patterns to fill in vertically, because we understand the patterns of voltages, currents, resistors across the circuit. But horizontally, we also know the relationship between voltage, current, and resistances. So, to see an example, let's say we're looking at the circuit like this. What is the current across the entire battery? So notice we have our battery here, 3 resistors. I'm going to set up my table. So I will always have my V. Oh, come on. VIR. In this case, I have 3 resistors, so I will call those R1, R2, R3, and then you will always add the R total or R equiv for equivalent. Fill out our cute table. And we always start by writing just what information we have. So I'll call this resistor 1. That is 2 kilo ohms or 2,000 ohms. So that's going to go under resistor here. Oh, ugly. Okay. Ohms. That's a 0. R2 is also the same. Now this is random that they happen to be the same. They will not always be identical. And the third one is also the same. All right. That's horrible, but sorry. So I also know the voltage of the battery, which we'll consider the total. So this is going under voltages, but under the total row. So that will be 12 volts. And that's all the information I am given. But I know that this is a series circuit. So I know some patterns here. In a series circuit, all the resistors add together. So 2,000 plus 2,000 plus 2,000 should give me the total of 6,000 ohms. I can fill that out here. Okay. Don't know anything about the currents. I only have one voltage. Okay. But I see that in this total column, I have my voltage and I have my resistor here. So going side to side, I can use Ohm's law, V equals I times R. This pen's not working well, to get that current. So current is also going to be found by voltage over resistance. So when I do that, I will have my 12 volts over 6,000. This pen's not working. So the current should be, let me get our numbers, should come out to about 0.002 amps. Oh my gosh. There we go. So technically, I think I'm done because it asks what's the current across the entire battery. So across the entire battery, we're looking at the total. I now know what that is, but for the sake of practicing, I want you to fill in the rest of the table, which we can do because in series, I know that all my currents are the same. So once I've found one current, I can fill in the rest, 0.002, oh my goodness, 0.002, 0.002. Okay, and then I have, well, I don't really have an option. To get these individual voltages, I now know my current and resistor. Again, I can apply Ohm's law. Current times resistance should give me voltage. So if I do that, 0.002 times 2,000 should give me 4 volts. Okay, and I'll see that they are actually all identical here. But that was random because each resistor just happened to be the same. To really check ourselves, if we add all the voltages, 4 plus 4 plus 4. In series, they should add to be 12 volts. And look at that. There they are. So here's one example on how to solve a series circuit problem using the VIR table.